Good morning or afternoon, everybody. Thank you for watching. This will be the first video in our series of remote lectures that will be working through the curriculum from our third unit of this AP Calculus AB school year. In this video, we're going to start off this third unit by looking at extreme function values, by looking at where a function becomes large or extremely small. We'll look at the tools that we can use to find that. We'll develop some vocabulary around that to describe those places and talk about the limitations of those pieces. We'll establish some techniques, and of course we'll look at a variety of examples that cover all the essential skills that you'll need to develop in here. Obviously it's not ideal for me to be home, but believe me, I would rather be with you. So, with that said, let's jump into the lesson. I'm going to teach it just like I would have before, but as with every one of the lessons this year, I've tried to improve on everything where I can. I always research a little bit beforehand and try to come up with good stuff. Hopefully this lecture will be no exception. So without further ado, I present to you what I hope is cNotes 16, Extrema. So, as we begin our lecture here, we're going to not let go of derivatives. Obviously, slope is still really essential. What we're going to do, though, is we're going to start using slope as more than just a tool to describe slope or rates of change. We're going to use it to describe for us behavior of functions. Now, you might ask yourself, as we get started, why would I want to know more about the behavior of functions? They're just little graphs and squiggles on my calculator screen. The truth is that's not accurate, really. It's kind of a short-sighted look at the way things work. In reality, what we want to be able to do is describe the behavior of real things, whether they be the velocity of a coyote racing along after a runner, or the speed of our car, or the amount of money we're taking in on a particular mutual fund. We want to be able to use function behavior to describe that and be able to figure out when is it most optimized. As in, when is it the largest value, which would give us in the money example the most money, or when is it the worst, in which case we'd probably be sell. So keep in mind everything here, although we're going to focus on it in a very algebraic and graphical sense here, everything here still does connect to the real world a little bit. We're just starting with a very mathematical picture of it, so that we can then build out from there. So to get things started, the way I figured I would build this out was the same way I have every other year for the last few years, and that is to just start with a very simple example to help kind of orient you to some of the thinking we're going to be going through here today. And the function I've given you is a very thoughtfully chosen function, but it is a polynomial x cubed minus 6x squared plus 9x. Now when you look at this function for the first time, you may just start to think about what types of things you know about it, like you're just prejudging the function. And one thing that I imagine at Franklin you might notice is that, of course, this is what we would call a positive noodle. And all that means is that it's an odd-degreed polynomial function with a positive leading coefficient. And that's useful because it does give us some information about the way the function looks. In particular, we know positive noodles start low and end high. The middle part is all dictated by what the function does, how many zeros, and what type of zeros they are, but at the same time we at least know the end behavior, which gives us a good idea of what this thing looks like. If we want to be more specific, we just need to factor it and develop more information about its zeros and intercepts. So we can actually do that though pretty easily. This is a readily factorable function. So I'm going to factor out a GCF of x. That leaves me with x times x squared minus 6x plus 9. And if you recognize that trinomial as a perfect square trinomial, or if you try to factor it, you'll eventually realize that our function f of x is actually equivalent to x times the quantity x minus 3 squared. The reason that's really useful is that if we were to set that equal to 0, we could very quickly see that this actually has two x-intercepts. X equals 0, which doubles as our y-intercept, by the way, and x equals 3, which we always call a bounce. So we could actually, with that information, sketch a really accurate picture of this particular function. And I'm going to attempt to do that right now. Obviously, it may not be perfect. So we got that. It says we said we're going to bounce off the x minus 3. Yeah, it looks bad. And there we go. There is what should be a reasonable picture. Notice it meets the qualities of a positive noodle. Starts going towards negative infinity on the left, goes up to positive infinity on the right, and then it approaches our two zero values in there. So that's a perfectly useful thing. Like, this is really great information. And in fact, if we focus though on this graph in the context of the questions I mentioned earlier, which is finding maximum and minimum values, like high and low points, like the best and the worst, the most optimal values that we can use, we can very quickly see where the minimum occurs. In fact, you can see that there is a minimum value right here at x equals 3. Now, it's not, using the word minimum value may be a little bit deceptive. It's not quite a perfect explanation for it, but we can see that there's definitely a minimum happening there. But of course, if I asked you to find a maximum point, you would look at this and might be a little bit worried. You can tell the maximum occurs somewhere up here, But just in looking at the picture, it's not clear what it is. Is it 1 or 2, or is it maybe some irrational value in between, or even a rational value in between? We don't actually know. But here's the thing. If we proceed forward with this expression, we can actually look at this function and figure out where that maximum is, or that, we're going to call it later, a relative maximum is. What we could do is we could focus on the slope at that point. So this is a polynomial, so we know it's differentiable. And unfortunately, it's not the best picture I've ever drawn. But take a look right there. If I draw a tangent line at x equals 3, you'll notice that the slope appears to be 0. Right? I mean, that definitely looks like the slope is 0. Simply because, oops, let me get this right. I want to copy that. The slope looks like it's equal to 0, because of course it's flat. And that kind of makes sense. It looks like our derivative is negative on the left side. Just if we drew a tangent line, it would seem to have negative slope. Positive on the right side, so it would seem to have positive slope. So the intermediate value theorem would guarantee there's a spot in between where the slope would have to be 0. Likewise, we can also point out that up here, wherever that maximum happens to occur, it also appears that the slope is equal to 0. So if we want to figure out where that actual special value actually occurs, at least at what x value, we should be able to find it by calculating out where the slope is 0. Well, we know, by this point, that if we're talking about slope of a function, that really means we're interested in its derivative function, which we'd call f prime of x. And calculating f prime of x for our situation here is not going to be too difficult. I'd focus on that first function, and then it's very quick. 3x squared minus 12x plus 9. Doing a little bit of factoring again, we'd have 3 quantity x squared minus 4x plus 3. And then you can quickly see that the derivative is 3 quantity x minus 1 quantity x minus 3. So I said supposedly we were going to find good information and tell you exactly where that maximum occurs. And we didn't quite yet, but think about this. If we're expecting the slope to be 0 at those high and low points that are in there, we could just set our slope function, or derivative, equal to 0. And then we could spit out a couple different values here. When we do, we end up with 2 different x values. X equals, let's see, actually I'll do this down below, I will. We get 2 different x values. We get x equals 1 and x equals 3. So those are the 2 x values that supposedly produce 0 slope on our graph. Well, look at that. We identified x equals 3 as our relative minimum just by looking at the picture. We knew the presence of that bounce, in Franklin terms, would lead us to a minimum. The second one we couldn't identify, but it looks to me like our second point is actually at x equals 1, simply because that is a spot where the derivative equals 0. In fact, it's the other spot where the derivative equals 0. So what we're seeing here is that x equals 3 seems to correspond to a relative minimum. And again, we'll formally define that term in just a second if you're not sure about it. And x equals 1 corresponds to what I'd call a relative maximum. So with both those two in place, in fact, we can look at our picture and we can very quickly figure out where those points are. We no longer have to wonder. And if we were curious what that relative maximum's y value was, we could just plug 1 in up here. In fact, very quickly, it would be 1 minus 6 plus 9, which is 4. So we could actually find that this point, this relatively high point is up there, is at 1, 4, and this minimum is at 3, 0. So what we're seeing here is one of the most important connections in all of calculus. It may not have been the initial piece that came out of the work that we've done, but it's an essential component of what's here. And it's something that I'm hoping is starting to sink into your brains, just even after that single example. So let me draw a beautiful, biologically accurate brain here. No laughter. And in this brain, let me point out the realization that you've hopefully started to fit. That is this. Derivatives give us maximums, or maxima, and minima. So in other words here, that's going to be one of our tools. And I don't want to make it seem like they give a lot of information about it. It's not quite that perfect, but it's an essential place to start. Basically, as part of our work, we're going to look at how the derivative gives us the tool that we need in almost every case to figure out where these relative extreme values happen to fall. In other words, they're going to be part of the recipe that it takes to calculate the best or the highest or lowest output of a particular function. So keeping that in mind as well, as we move forward, I'm going to keep using different words to describe things. Obviously, I'm going to use maximum and minimum to describe single high or low points respectively. I'll use maxima and minima to describe plural, so multiple maximum values or minimum points. And then finally, if we're going to talk about both of them together, we're going to talk about what the title of the lesson is, which is Extrema. And for some reason, whenever I say extreme, I always want to say extreme. I don't know why, it just comes out that way. It's extreme. But in our case, when we say that, we're basically talking about maxima and minima. So it's just a fancy way to describe them at the same point. That way we don't have to say high or low points, or high-low points, because maybe that means something else. So with that said, we're ready to jump into our work here. We've seen how, we've kind of gotten the gist of what's there, but it's about time for us to kind of formalize this a little bit and define what it is that we're talking about here. Okay, so now that we've established that there is some sort of inherent connection between high and low points and the derivative being equal to 0, or at least something happening with the derivative, I want to formalize these things a little bit and talk specifically about the vocabulary to describe these sorts of high and low points. So in order to do that, we need to give them a name and then, of course, define them formally. So we're going to call these places relative or local extrema. And when you hear that term for the first time, especially that phrase local, it likely makes you think about something that's kind of like a tight community. It's really close together and small, as in like local news describes the immediate community and people around you, whereas larger news or global news might describe more than that. So we're talking about the ability to find a high point relative to a small area. And that's exactly what we have here in our definition. So let's see if I can do this right. Boom. So what we're going to define first is what we're calling a relative maximum. So we're going to say that the function f has a relative maximum at x equals c if f of c is greater than or equal to f of x for all x values in an open interval ab containing c. So I realize there's a lot there, a little bit to process, but for the sake of time I want to keep moving forward. Keep in mind that these notes will be posted so you'll be able to access them later if you miss parts of the definition. I really want to talk about what this definition says though. And to do that I'm going to use my red pen feature. So in here, it mentions first that we have a relative maximum at x equals c if f of c is greater than or equal to f of x. Well, in a sense, what that's saying is f of c is bigger. So I mean, just translate that. F of c is larger than the f of x or y values for all the x values in an open interval. So we're saying f of c is the biggest. Then we're saying it's true on an open interval containing c. So let's take, for example, our function over on the right side, this function f of x, which I've drawn and contrived perfectly for this scenario. So if you look like I at this function, you can find that there is one relative maximum for f of x that we have here. Go ahead and say it out loud. What is that x value? That's right. The relative maximum is x equals 2. I got you to interact with the video. So the relative maximum is at x equals 2. But the truth is, if we look at x equals 2, you can see that it's not the absolute largest value that's out there. There are larger values right here, somewhere off to the right side. But it's still a relative maximum for our function because we can draw an open interval containing our c value, which in our case is 2, and we can say that's the highest value in there. Take, for instance, that particular interval. Maybe that's going from -1 to 3. We can see that the highest point in that interval is clearly at 2, f of 2. So what we can say here, in our example here, our local maximum, or our relative maximum, and you'll see both names used interchangeably, I'm literally going to switch between those names all the time, is going to be the point 2, f of 2. So an important thing to get there right off the bat. So we found where that happens. Now likewise, we've just talked about high points. We can also talk about low points. So the corresponding definition would be for a relative minimum, or relative minimum. That would be that f has a relative minimum at x equals c if f of c is less than or equal to f of x for all x values in an open interval ab containing c. So in this case, notice that the big change here, I mean everything is identical except for the name and that statement, the inequality. It says that f of c is less than or equal to f of x for all those x values in an open interval. So in here, if f of c is less than or equal to f of x, we're saying that it's smaller relative to the points around it. And in here, the nice thing is in our particular problem, we actually see that there are not one but two relative minima that appear in this particular function. So one relative minimum occurs right over here on the left side, somewhere between -6 and 0. And the neat thing here is I may not have emphasized it the last time, but there are lots of closed intervals, or open intervals, that we can draw that would make that still be the relative minimum. Maybe not right there, but right there. We can see that's a low point relative to that open interval. So basically, once again, we can draw that. So that tells us in this particular problem, we have one relative minimum at -4, f of -4. So let's point that out here as well. So we have local or relative mins, just to use that name a little bit. You'll see my abbreviation, it's an acceptable abbreviation. We have a relative min at -4, f of -4, as we just said. But then, of course, we've got another interval we can draw. If we go over to this side, we actually have one at x equals 4 as well. So we have a second relative minimum at 4, comma, f of 4. And you can kind of see what makes a relative minimum or relative maximum valuable explanation or name to be able to give to a function or to a part of a function. Because if we're talking about maximum, the implication is just the biggest possible thing ever. We've already shown with our first local maximum that it wasn't actually the biggest thing we could get on this function as we can see it. It was just a relative high point. It's like when you're climbing up a mountain. There may be relatively high hills that you have to reach en route to reaching the top of the mountain. Sure, the high point may be at a certain spot at the end, but that doesn't mean that there aren't some strenuous, like grueling hills to climb up along the way. So keep that in mind here. Like these you can have multiples of. It's a really powerful thing to be able to get. You can get more than one as you look here. Now, before we move forward and start to talk about how to actually find these, I'd like to point out one more thing. The vocabulary isn't just to be able to say the local maximum is an ordered pair. There's actually 3 different ways that you could be asked to identify and talk about a relative or local extremum. So we've talked about when you're asked to find the local maximum. If it says the local maximum or relative minimum or relative minimum, any of those things, they're just a safe way to do it is just to describe the entire order pair, 2, comma, f of 2. And if we knew what f of x was, we could literally put what the y value comes out to be. So in here there are 2 other ways we could also say. You might also be asked for, or you might also say that the relative maximum is at x equals 2. In which case we'd be talking about the x-coordinate of that relative maximum in this case. Likewise, you also might be asked what is the local maximum value of the function, and the implication with local maximum value is that you give the y value. So, kind of tough, but one of those things you have to do here is you have to read the question carefully, because I feel it's an important thing. Like you're either establishing the location of where it happens, or what that actual high or low point happens to be. And of course I did these for maximum. We could just as easily do them for minimums. Like we would say for the relative minimum down below, the relative minimum is at x equals -4 to get its location, and the relative minimum value is f of -4. So those notations work just well for both different things that we're going to actually hit. So now the question, having established these kind of formal ways of thinking about relative extrema, the formal question that you'd want to ask is now, okay, so we know that they exist. Now, how do we find them? Like, what is an expedient way to efficiently and correctly find all the places where these relative extreme values will occur? So especially awkward because, of course, as we saw in the previous one, there's lots of different open intervals we could choose. So you might be wondering, how do you find there? Well, the truth is we actually previewed this on the first slide of the lecture, the first page that we worked on. What we're going to be searching for are points or numbers, depending on the situation, called critical numbers. And we're going to focus on critical numbers themselves rather than worry about the y value themselves. So for a function f of x, x equals c is a critical number of f of x if f of c exists and either f prime of c is 0 or f prime of c is undefined. So take a second to kind of soak that in. So keep in mind too that when we say critical numbers, the word critical isn't like, I don't like your movie, it stinks. It is more like critical as in important. It's vital, it's critical that you turn in this assignment or give this money to the bank by 4 o'clock. Though that kind of critical. It's very essential information. So what's going to be tough about this definition is it doesn't mean every value that's important or worthy of interrogation or looking is here. It just means these are particular places. And in a sense, what we're really finding here is we're finding all the candidates. Like that's really our tool here, is we're trying to find the candidates, some candidates, or the candidates for our particular situation, some candidates for relative extrema. So this is our recipe. We want to find where those potential values are. Now to point this out, there's a couple different things here. So the first thing that I want to note is that it says that f of c must exist. And this is an important one for me to note because in past years I haven't always made a big deal about this. I've been focused on the output rather than the definition of critical numbers. But it does say that f of c has to exist. What that means is that if you've got a function that has a vertical asymptote at, let's say, x equals c is not a critical number. And that feels really weird to me because it's still a really important point, especially when we get later into this unit and start to analyze function behavior more deeply. But the truth is, because that function value, that x value is not in the domain of the function, we can't talk about it as being a critical number the same way. It's just something else we might have to note. So keep that first part in mind. Second, we note in here that it mentions that one of the two ways that you could get that to happen, the derivative could contribute to a critical number, is if f prime of c equals 0. Well, we saw this on the first page of the lecture pretty effectively. We were looking at something, I think, like that. Actually, I'll just draw a fake one. We were looking at something like that. Well, keep in mind, if f prime of c equals 0, then of course what we're getting are places where there's a horizontal tangent line. So let me even put that in there, horizontal tangent line. Now we'll discover in a few days that horizontal tangent lines can sometimes occur at a place where there's not a maximum or a relative maximum or relative minimum, but at the same time those zero slope spots are really prime candidates, get it prime because of derivatives. They're really prime candidates to have a particularly high or low point occur. So keep that in mind. Finally, the last piece that sometimes messes with people, and I can understand why, it becomes really forgotten, is that f prime of c is undefined would also give us a critical number. But keep in mind, f of c has to exist. So once again, the vertical asymptote doesn't give us a critical number, but if f of c exists and the derivative doesn't, then we have a still potentially critical number. And I'm thinking that you already can visualize why this might be just by picturing one of our favorite types of functions. What function did I just draw? That's right, it's an absolute value. In the absolute value of x function, looking here, we know that there is a spot where the derivative doesn't exist. Y prime of 0 does not exist. There's what we call a sharp turn there. But of course, looking at an absolute value function, you can tell that that corresponds to a relative or local minimum. So the truth is, we have to consider the possibility of f prime being undefined, because if there is a sharp turn, that sharp turn absolutely could lead us to a place where there is a relative minimum or maximum. So basically, all those pieces of critical numbers are there. We're going to work on finding critical numbers in just a second. But before we do, I want to reveal one more cool piece of information. Because you might say, well, that's great and all. Critical numbers are nice, but I mean, what other things are out there? Like, surely there's more that we have to look out for, some other special case. This theorem down below is not one that you're going to know. It doesn't have a fancy name or anything, although we'll hit one of those later on in the lecture today. What it says, though, is that if you're at a relative minimum or relative maximum, then you have to be at a critical number. As in, this is saying critical numbers alright, I did that in the reverse. Let me reverse that. Relative extrema, so in other words, our relative high or low points relative to some open interval, relative extrema only happen at critical numbers. So keep that in the back of your mind too. It's good to know. Like basically, if you know that you're at a absolute or a relative maximum or relative minimum, you'll know that you're actually at a critical number. And again, it sounds humorous to say, but that's not as critical as everything else, but it's a nice thing to know. Those are critical numbers guaranteed. There may be more, but at least we know those ones are critical numbers. There's not some other thing that can happen at a relative max or min. So with that said, let's practice the actual technique. So because very often you're going to be asked to find those critical numbers, and the nice thing is that this is just a nice application of the work we've done in the past with differentiating. So our first example here asks you to find the critical numbers of f of x equals 4 over x squared minus 5x. And again, as you hear that, that should lead you to realize that your goal is to figure out where f prime of x equals 0 or is undefined. So in particular, kind of looking for a sharp turn sort of thing. So in looking here, before we do anything else, let me point out that looking at this function, I can tell automatically that there are actually two x values where there's going to be a vertical asymptote. Specifically, those two values are x equals 0 and x equals 5. So right away, we know those values are not critical. It's not that they aren't critically important, but they don't meet the definition of this thing we're calling a critical number. Critical numbers have to be existing on the original function, and clearly plugging in 0 or 5 for x gives you 4 over 0 in both cases. So just keep that in mind. We can't get those as values, so don't get overexcited if they show up. We're looking for other x values that make the derivative 0 or undefined. So let's see. In order to get there, I need to take the derivative of what f of x is. To help me, I'm going to rewrite this function in an easier to read form. So this is 4 quantity x squared minus 5x to the negative 1. And when I see that, that makes me think of the chain rule. You thought you could escape the chain rule. Mwahahahahaha, you could not. So with that as our function, we can, of course, break this apart. We can do some decomposition work. So let's see. We've got, if we're going to let u equal the inside, I'm going to let u be x squared minus 5x. F of u will then be 4u to the negative 1. If we differentiate each component here, we're going to get negative 4u to the negative 2. And of course, u prime will be 2x minus 5. If we bring this stuff together, we can quickly get that f prime of x is going to be equal to negative 4 x squared minus 5x to the negative 2 times 2x minus 5. And more specifically, if I write this in a slightly nicer way, we'll get that this is equal to negative 4 quantity 2x minus 5, all divided by x squared minus 5x to the second. So with that in mind, there's our derivative. That's the first essential step of finding any critical number. Now we need to figure out where this is 0 or undefined. So first, to save us a little bit of work, if we plug in 0 or 5, of course we're going to get an undefined derivative, but those are the only two values where that'll happen. And we already noted that vertical asymptotes occur there, so those don't count as critical numbers. Instead, if we set this equal to 0, the only thing that's going to contribute to our critical number is going to be the 2x minus 5. And that's going to lead us to right away that we're actually solving negative 4 2x minus 5 equal to 0. And very easily you can see that x equals 5 over 2, or 2.5, is going to be our one value. So that means that we have only one critical number for this function f of x, and it occurs at x equals 5/2. So you can see in my work where I'd be looking was correct derivative using the correct technique. In this case it was the chain rule, setting it equal to 0, and then identifying the correct value itself. So pretty straightforward, but definitely an essential skill to go through. Likewise, another way this question could be asked that kind of throws a little bit of a wrinkle in there is you could ask the question from a different starting point. So it says if the derivative of f of x is given by f prime of x equals that thing over there, what are the critical numbers of f of x? So in this question, we don't necessarily have enough information to know for sure what's happening on the original function. Like theoretically, something else could be happening that contributes a little bit. But as I look here, it looks to me like we once again have a vertical asymptote at x equals 5. And although we can't guarantee that there isn't maybe say a vertical tangent on the original function, the vertical asymptote at x equals 5 tells me that likely we're going to have a vertical asymptote on the original. So in other words, I'm thinking that's going to be not critical here. So that's just my assumption. Again, I could be wrong, but I'm not in this case. The second thing, though, we need to look at is we need to figure out when is f prime of x equal to 0, because that would lead us to the critical numbers. The nice thing about this problem, though, is that they already told us what f prime of x is equal to. It says it's equal to this rational expression. So in other words, we just want to figure out when is x squared plus 10x over x minus 5 equal to 0. So thinking about this for a second, just as we did in the previous one, we know that that's going to be focused on when the numerator is equal to 0. Because as we said, the denominator contributes to the vertical asymptote, not really the zeroness otherwise. So doing a quick little factoring workshop here, we get x times x quad plus 10 is equal to 0. And that means that we have, it looks like, two critical numbers. X equals 0 and x equals negative 10. And again, the cool thing about this particular problem is we don't even know what f of x is. In fact, getting to f of x would be pretty challenging. But at the same time, we didn't need to, because we know that a critical number is when the derivative is equal to 0 or undefined. And that's enough information for us to proceed forward and find some critical numbers. Okay, so that brings us then to the final question that I'm going to talk about critical numbers with, but I will say this is probably one of the toughest critical number questions I've ever asked before. I just know that I'm considering asking these questions in the future, and you'll even see them on your assignment tonight as well. So I'm asking you right here, or we're talking about trying to find the critical numbers of the function f of x for this piecewise function right here. Now, it's not the world's most difficult piecewise function, but obviously there's a lot of extra things you have to think about when dealing with a piecewise function. In looking here, of course, if we're talking about critical numbers, it's important to remember that in order to have a critical number for f of x, what we need are two separate things, or we need to verify two separate things. First, we need to make sure that f of c exists. So we need to make sure that any point that we choose, the function value is well defined there. Now in our particular piecewise function, this is going to be given to us automatically simply because x is less than or equal to 2, so 2 exists, and both of these are polynomials. So everything's going to be fine there. We know the function values will exist, just a matter of the other property. And that other property is that f prime of c is either 0 or undefined. And that's going to take a little bit more to find. So we need to actually focus our attention on that second spot. So to get there, as you've probably figured out, when you're finding critical numbers, the most important step is to compute the derivative. So let's calculate the derivative for this particular piecewise function, something you've done plenty of times. Derivative of x squared minus 1 is 2x. So our derivative for f prime is going to be 2x when x is less than or equal to 2. And then the line 3x minus 3 makes up the right branch. So that means the derivative is just 3 when x is greater than 2. So there is our derivative. Now, of course, with a derivative, an easy place to start is to ask, when does that derivative equal 0? Because that's a good place to begin your work. Well, in our case, because we have two branches, there's two potential places we need to consider. First, we need to see when 2x equals 0, and second, we need to see when 3 equals 0. Well, 3 and 0 are different numbers. Otherwise, I've got $0 I'd love to trade for your 3. So that's never true. But 2x equals 0 does imply a single x value, particularly x equals 0. Now, x equals 0 should be a critical number for our function unless x equals 0 is not in the section of the graph that this portion of the function is defined. So we were looking at the parabola part that it gave us x equals 0. Notice that the parabola occurs when x is less than or equal to 2. Since 0 is less than or equal to 2, that does tell us that we have one critical number at x equals 0. So we've got at least one in our situation here. It's a really important thing. And in fact, the truth is most people would stop right there and just say, well, yep, we got our one. Good job. We got a critical number. Good job us. Unfortunately, though, with piecewise functions, as you should already know, there are lots of issues that come up with even the best behaved piecewise functions at boundaries. Because even a boundary that meets might not meet in a smooth way. It might have what we like to call a sharp turn or a cusp or whatever you want to call it. So the truth is, before we can move forward, we may have taken care of the f prime of c equals 0, but we need to pay attention to whether or not the derivative might not exist at a particular point. And as we said before, with two polynomials, the only place where that could occur is the boundary. So the other thing we're going to have to check in order to find a potential critical number is to check the differentiability at the boundary. And our boundary in this case happens to be x equals 2. So keep that in the back of your mind as you look here. So we want to check the boundary. So in order for a function to be differentiable, it must have both the function continuous at that point and the derivative continuous at that point. So let's check both of those two things. First, let's check to make sure the function is continuous at x equals 2. Now, we've said before many times there are three properties that are required to be satisfied, but the one that's most restrictive most of the time is to check that the left-hand and right-hand limits are both equal, allowing the limit to exist. So what we're going to do is we're going to check the limit as x approaches 2 from the left side and see if that's equal to the limit as x approaches 2 from the right side of f of x. So easy enough to plug into. There's our function. If we plug 2 in, we'll have 2 squared minus 1. On the other side, we'll have 3 times 2 minus 3. That's going to give me 4 minus 1 and 6 minus 3, in which case both times we get 3. So although there's more we could say to be even more formally accurate, what we've just found is this function is definitely continuous. The function does meet at x equals 2. So there's not going to be an issue with differentiability because the function doesn't come together there. So very good start. Second, though, we want to check for the smoothness, in a sense, at x equals 2. So in this case, I'm going to say continuity of f prime. Because it's not enough to just say the function is continuous at x equals 2. We need to make sure that the slope is continuous there too, so that it comes out nice and smooth. So in our case, that's an easy transition. We're going to take the limit as x approaches 2 from the left side of f prime of x, and see if it's equal to the limit as x approaches 2 from the right side of f prime of x. So again, we're using the slopes this time. So using our slope function, that's going to be 2 times 2 on the left, and it's going to be 3 on the right. So our question is, are those two equal to one another? And unfortunately, no. 4 does not equal 3. So what that tells us is that we do have a point which we're going to call a critical number. So since f prime of 2 does not exist, because what we just showed was that it's not equal to, it doesn't produce the same value on both sides, that implies 2 is a critical number. So after all that work, we can now finally draw our full conclusion together. We can say it, put it all into one place. We have that there are 2 critical numbers. So those 2 critical numbers are x equals 0 and x equals 2. And of course, what's interesting about this function is it doesn't mean that it necessarily has it doesn't necessarily have a maximum or minimum there. In fact, if you were to just try to think about what this picture looks like a little bit, I think you'd be able to very quickly figure it out. It actually looks something like this. And right there is not actually a maximum. It just goes high and then it breaks off and starts going even higher. So it's not a maximum, but it is a critical number. And remember, critical numbers don't only occur at maxes and mins. It's maxes and mins that only occur at critical numbers. So interesting little work. That gets us through kind of the hardest you could possibly run into for a critical number. Although I think I got some good stuff on your assignment tonight too. Okay, so now that we've talked a lot about how to find relative extrema, either relative maxima or relative minima, or their corresponding names local maxima and local minima, the truth is we're finally going to come back to something that I kind of said earlier and just kind of threw aside, that I didn't spend a lot of time thinking about. And I'll remind you of what that was. When we were talking about a relative maximum, I pointed out that 2, f of 2 was a relative maximum. It wasn't the highest point though. There are higher y values out there. And I pointed to the fact that there were points on this little area over here, between what we said, like 5 and 7, that had higher y values. So the truth is, well, I'm sure you nodded along and wrote it dutifully in your notebook that the relative maximum occurs at x equals 2. I might argue with you now, retroactively, that that can't be much of a maximum if there's literally other higher values that we can see. And truthfully, like, that's an absolutely valid point. Who cares about these relative high points? If you're trying to climb Everest, don't climb Everest. It's super dangerous and expensive as well. Dangerous for everybody. Like, I think a third of the people die when they're trying to climb. Aside. So, don't celebrate and take photos on top of the little baby hill when you're climbing. You take the big pictures when you finish the whole thing. Otherwise, people are like, well, what's your problem? Like, you're like, oh, I hit a relatively high point. And nobody's going to respect that. So instead, my point here is that although we looked at relative extrema before and found that they had a really nice pathway to finding them, they aren't the only type of extrema out there. And it's extremely important that we point out the other type that's out there, because these ones are just as useful and sometimes even easier to find. So these ones aren't called relative anymore. These are called absolute or global extrema. No, I can't spell the word global. Yeah, so before, when you hear things like relative maximum, you might be thinking about your aunt or your cousin or something. In these cases, this is absolute maximum. These are the biggest possible things you could get, or the little tiniest thing you could get. Just depends on what you have. So keeping that in mind, in this case, our definition looks very similar, but there's some very subtle and important differences between them. So let me pop out the first one. So, and it did not take my little line segment. Oh, that's too bad. Oh well. So it says here that f has an absolute, or global, maximum at x equals c if f of c is greater than or equal to f of x. So basically, up till that point, you're like, this sounds exactly the same. F of c greater than or equal to f of x. We're saying f of c is the biggest y value there for all x in closed interval ab containing c. So in this case, we're no longer looking at just any open interval. We're looking at the closed interval. So if you're on a closed interval and that's the biggest y value you get, that's the maximum. None of this little, like, silly, on a small interval, like, oh, in my neighborhood, I'm the best. No, we want to talk about the entire neighborhood. This is overarching everywhere maximum. So, and of course, looking here, as we've done in the first example, if we're looking at our particular situation here, the absolute maximum, there should be one. I mean, technically you could have more than one, but we're looking for the biggest y value. In looking up here, and let's say that we're on the interval. Let's just go from -6 to 7, since that's what we can see. On -6 to 7, our absolute maximum is going to be, well, let's see where. Well, let's see if we can find the highest point. Looking at our picture, looks to me like our highest point is very easy to find. Interestingly enough, it looks like our highest point is the point 7, f of 7. But that feels weird, right? That high point isn't even a max. It doesn't have that nice, like, bump. Its derivative isn't anything. It's just like an endpoint. Absolutely right. It's an endpoint. Basically, when you stop a function's growth, there's a possibility that it could have been going up for a while and then you just cut it off, in which case the highest point might have just been when you stopped. Like, there's all sorts of things that happen that way in the real world. And in this case, the right endpoint turns out to be our absolute maximum. Now, likewise, we could talk about absolute or global minima. I lost the letters IN here. That's interesting. It looks weird, but oh well. So in this case, it says f has an absolute minimum at x equals c if f of c is less than or equal to f of x, so in other words, the smallest y value, for all x in a closed interval ab containing c. So it's the completely analogous definition here. We're looking for the smallest y value along some closed interval. So for instance, if we look on the interval from -6 to 7, our absolute minimum or global minimum, let's see, the smallest y value, interestingly enough, that relative minimum we had at our lowest point before on our left side at x equals -4 turns out to be our absolute minimum as well. So the interesting thing to pull out of this is, of course, on a particular interval, a relative maximum or minimum could be the absolute maximum or minimum, but it might not. It's not guaranteed. Like, one does not guarantee the other. So now a couple things to point out. We chose the closed interval -6 to 7 just to kind of focus our attention on. But if I'd changed and started in a different location, we could have changed that value. In particular, if I wanted my closed interval to run from -4 to 4, then our absolute minimum would be the same. It'd be at -4. But our absolute maximum in that case would be at x equals 2. So the interval does matter as well. So don't get obsessed with the idea that it's always going to be a certain point or that it can't change, that there is some absolute maximum for a function. Obviously, sometimes there is, but that's not always going to be the case. So instead, just keep that in the back of your mind here, that the interval we choose matters, but it's not a coincidence that we actually chose closed intervals. And I say that, moving forward, because as we look at this next example, it's possible that you can change the interval and radically change the existence or presence or location of an absolute maximum or minimum. So in particular, I've drawn 4 different grids, and I've labeled absolute max, absolute min. I don't think this is something you necessarily have to write down, but obviously if you feel up to it, you can. I'm just going to work through it pretty quickly because I think it'll illustrate the concept for you of how essential the interval choice actually falls. And in our case, we're going to choose a really simple function. We're going to choose y equals x squared. So in this situation, choosing y equals x squared, I'm going to graph it really quickly, but notice I'm establishing our analysis of x squared on 4 different intervals, like that alternately choose between the left and right endpoints being open or closed. So if I graph 0 to 2 for x squared, we know that it has its vertex at 0, and then it increases from there. So in here in the closed interval, it's going to look like this. So our absolute maximum, pretty easy to find. It's going to be the point 2, 4. And I say 4 because, of course, 2 squared is 4. And our absolute minimum, very easy to identify as well, is going to be 0, 0. By the way, I don't know if anyone else sees this, but I sure see a face there. Can make it look evil. Sorry. Ha! It's like the Grinch. Okay, so there's our absolute minimum. So same function this time, but in this second one, in B, what if I make it on an open interval? In this case, the absolute minimum we wanted at that vertex 0 is no longer there, so there is no absolute minimum, and the absolute maximum that we wanted to be on the top is no longer there either. So in this case, just by removing the endpoints, we actually have no extrema whatsoever. There's no absolute high point or absolute low point. Moving to the left side, if we eliminate just the right endpoint, as in we start at the vertex and then we go up, pretty easy to predict what happens. We lose our maximum that was supposed to be at the high point, but our minimum now has returned as the origin, 0, 0. When we flip that, though, and start with an open dot and then extend up to the high point, obviously our maximum is once again at 2, 4, but our minimum has been removed from the domain of the function. So in this case, what's kind of interesting to pull out is the fact that depending on your interval, the same function can have or can have a particular maximum, or it could have a different one, or it could even have none. But you'll notice out of these 4 intervals, there's one interval that we had both an absolute maximum and absolute minimum. And that interval was the first one. And what type of interval is that? That's a closed interval. And remember in our definitions here, actually I'll leave that circle. Remember in our definitions 1 page ago, we noted that you have an absolute maximum if you're in the closed interval AB and that value is the largest, or you have a minimum when the closed interval value is the smallest. So in this case, that closed intervalness actually leads us to a really important theorem. One that we're not going to be able to prove here, and that you probably don't want to prove from having read through it earlier today, but one that actually tells us how we can guarantee that there's going to be an absolute maximum or absolute minimum. Okay, so to try to answer that question of how we can guarantee that we have an absolute maximum or absolute minimum, we look at our second of three value theorems. So this is the new corresponding theorem to go along with the intermediate value theorem. So this is called the extreme value theorem. And if you're like me, when you say it, you might want to say extreme value theorem, just because it sounds more extreme. So in this case, what does the extreme value theorem say? It says that if f is a continuous function on a closed interval, then f has both maximum and minimum values on that interval. So let's break this down into components here. Like what it says, f is continuous. So the requirements to use this extreme value theorem itself, first requirement is that we have continuity. So your function has to be continuous. There can't be any jumps, there can't be any breaks, there can't be any vertical asymptotes, there can't be any holes. Second, it says it has to be on a closed interval. So in other words, we have to be analyzing a continuous function on a closed interval. In this way, we're basically looking at the same requirements more or less as the intermediate value theorem. Like they're very similar at least. In order to be eligible to continue forward, we have to be on a closed interval and a continuous function. So after that, then what it says is if you have those two things, then f has to have both a maximum and a minimum value on that closed interval. So thinking about this, we already saw this on that first example we were looking at, but just kind of picture a function. Like let me sketch on, let's go from A to B here. Let me sketch some sort of continuous function. Doesn't really matter what it is. So there is a continuous function on that closed interval. We're looking for a minimum and a maximum value. Absolute minimum. And it looks like absolute maximum. So they're there. Likewise, this one always threw people. This one always cost me for a little while. So let's say that we're looking here. This one might mess with you. Let's say we start here. We end here, and we have a constant function. So people might go, see how you're going to have a maximum or minimum there. Well, the truth is, since maximum and minimum both require simply, we'll go back a little bit here, they require f of c to be either greater than or equal to, or less than or equal to, all the other x values. In this case, any x value in a to b would provide both the maximum and minimum value. In a constant function, both max and min happen to be the same thing. So basically here I might say that this is max and min. So all of them have that. Over here we said this was min and this was max. So now we've seen what it looks like with a continuous function on a closed interval. You might be wondering if that continuity thing is really that required. We'll take a look at this situation. So let's look at this one. We're going from A to B. So in this case, you can clearly see that f is not continuous. Like you can tell that there is a jump somewhere on the left. Like let's imagine it that it's at -1. Well, because of that jump, although there is a maximum value on here, the minimum value is trying to occur right down there, what we said was -1. But because we're not including it, which is allowed by the discontinuity here, that tells us that there is no minimum. So right off the bat, we can see that that closed interval portion is an essential component of the extreme value theorem. It has to be there. Likewise, just to wrap this up, if it questioned you for a second about whether or not you need to be on a closed interval, like why would you require a closed interval, that's actually really easy. We saw it in the previous page, but we can draw another example of it. If we're going from here to here, and we're on the open interval from A to B, there's no minimum, and likewise, there's no maximum. So because there's always a possibility that our absolute maximum and absolute minimum can occur at the endpoints, we need to make sure that we're on a closed interval. Otherwise, we can't guarantee you that there is an extreme value for that particular function. So basically, to use the EVT, the requirements are, as we said, continuity. And again, it just needs to be continuous on that portion of the function. It doesn't have to be continuous everywhere, just inside the portion that's required. And it has to be on a closed interval. Given those two pieces, you can guarantee that there are max and mins. And of course, by max and mins, we mean absolute max and mins. Like sometimes when you don't see anything mentioned, the implication is that you're talking about global or absolute max or mins. And that's the truth here. Like there may not be a relative maximum or minimum because that's a little bit more restrictive, but there will absolutely be an absolute maximum and absolute minimum. So with that in mind, the next question might be, well, that's all well and good, but I don't care that we're guaranteeing there is one. I actually want to find them. Like, what is the recipe to find absolute extrema? And in fact, I should write that in here. I'll write global. So how do we guarantee that we can find global extrema? Well, now, in order to get here, a good place to start is to think about the examples we've looked at already, and to realize how it is that you can end up with an absolute extrema, or an absolute extremum. So take a look at our expression over here. In one case, let's just kind of note these pieces here. In one, our absolute minimum happens to occur right down here, which happens to also be a relative minimum. So in this case, one way that you can get an absolute minimum is by finding a relative extremum. On the flip side, if we look over on the other side, our absolute maximum occurs in this particular example. Our absolute max is not at a relative maximum, but it's at an endpoint. So truthfully, what we're seeing is that there's two different ways that we can end up with an absolute or global extremum. We could be at a relative extremum, or we could simply be at an endpoint. So basically what the moral of the story is, if you want to find global extrema, I'm going to just put to find them, you have to consider both relative extremum or relative extrema. Geez, I'm having trouble pluralizing. Consider both relative extrema and endpoints. So in other words, what we're going to do here is going to be actually pretty straightforward. It's a really important skill, but it's very easy to execute. Basically what we're going to do is we're going to try to find and check all of the potential relative extrema and the endpoints to see which ones are biggest and which ones are smallest. At least once we know have a continuity. Now remember though, to find the endpoints, that's easy. The endpoints are given pretty much always. On the flip side, to find relative extrema, if you'll recall from maybe 15-20 minutes ago, we said that all relative extrema occur at critical numbers. So what we're going to do is we're going to find the critical numbers for a function, we're going to find the endpoints, and then we're just going to check for relative size. Or forget check relative size, that's a fancy way of saying compare size. So we'll just see which one's the biggest and which one's smallest. So this process that we're talking about has a name, and in this process we're going to check all of these potential values. The process we're going to follow is called the candidates test. And I like to think of it as kind of like a debate of sorts. But for the moment, it's just nice to know what the name is. There's not really a definition that goes with it. I'm just going to show you how to use it. Because in a sense, it does all of this stuff. It locates all the potential places where we could have a maximum or minimum, and then it checks their relative sizes, or compares their sizes. So it's called the candidates test. So to do it, let's take a look at an example. So we're going to find the absolute extrema, so both the absolute maximum and absolute minimum, of f of x equals 3x to the fourth minus 4x cubed on the closed interval from -1 to 2. Now keep in mind, this is definitely a non-calculator question, simply because if we had a calculator, we could just look at the picture and find the highest points. In this case, the goal is to have you do that analysis without actually seeing the function automatically. Although, we could probably express this and factor it and graph it out and see a good picture of what's there. Before we start, it's worth considering for a moment the extreme value theorem. And you might ask yourself, what does the extreme value theorem guarantee us here? Well, in this case, f of x is a polynomial, and polynomials are differentiable and continuous. So that implies f is continuous. In our minds, although there's nothing we have to say here necessarily for this particular case, what that means is that f is going to have both a maximum and a minimum on the interval, the closed interval, -1 to 2. Because the extreme value theorem says, if f is continuous on a closed interval, then it will have a maximum and a minimum. So keep that in mind. Because of that, we're guaranteed to have a maximum or minimum here. It's only our job to find it. Now, once again, as I said, we're going to perform the candidates test. And candidates test itself involves some steps. So I'm going to go ahead and list out the steps here just to kind of help you organize your thinking. But again, I think this will become second nature for you. It's a really essential skill in the course. So the first thing you're going to do is to locate all critical numbers. And the reason I say that is because we want to find where those relative extrema actually occur, because each of those could potentially be the absolute maximum or absolute minimum. So let's do that. So to do this, of course, to find critical numbers, we have to find the derivative. That's pretty easy in our case. That's 12x cubed minus 12x squared. Doing a little bit of factoring. Actually, you can factor out a lot here, can't you? You can factor out a 12x squared. That'll leave us with 12x squared times quantity x minus 1. If we set that equal to 0, again, we get two critical numbers. We get the critical numbers x equals 0 and x equals 1. So there are two critical numbers. Each of those is a candidate. In a sense, if we're thinking about this, I mentioned a debate earlier. In a sense, this is like them putting their names on the ballot. By qualifying as critical numbers, that's like them paying their fee and getting their name printed onto all the ballots that are come out later. They're now eligible to run for absolute maximum and absolute minimum. So we did the critical numbers. That step wasn't too trying. The next step is even easier. Second step is to find the endpoints. And in a sense, I almost consider this step a joke, but it's so easy to forget about the endpoints just because we're so focused on the calculus, the intense calculus of finding critical numbers, that it's sometimes easy to forget that we need to include the endpoints. So we found the criticals. In our case, the endpoints are given to us. We have x equals -1 and 2. So, and in here, by the way, it's always worth pointing out that as you're doing the critical numbers, you need to make sure that they actually fall in the closed interval we're talking about. In our case, we got 0 and 1. 0 and 1 are both safely between -1 and 2, so we have to consider them both as candidates. But if one of them, like say for instance, we had gotten 42 as our critical number. Sad as it would be, although 42 is an excellent candidate, 42 is not in a closed interval, so 42 is not eligible for the particular election we were looking at. It'd be like if 42 was a 16-year-old. Like, you might be a great candidate as a potential leader, but you're not eligible to run for president. That kind of world. So we've got critical numbers, we have endpoints. The next thing we're going to do would make one of my favorite characters on television happy. We are going to make a table. I was thinking about Ron Swanson in Parks and Recreation, by the way. So in order to compare these values, there's lots of ways to do it, but truthfully, I like this making a table strategy because it organizes your work so effectively. Because what we're about to do is we're basically going to figure out what is the y value at 0, what is the y value at 1, what is the value at -1, and what is the y value at 2. And then we're just going to say which one's the biggest. We're going to compare, basically. So having a nice organized strategy to show off those values just allows us to make that comparison really quickly. So in here, our table looks like such. We're going to compare x values to values of f of x, not f prime of x. Keep in mind, we don't want to find the biggest slope value. That actually means something else. It's called a point of inflection. For us, we're looking for the biggest f value. So we're going to be looking at the y values, or f of x values, for 3x to the 4th minus 4x cubed. So in our table, we're going to plug in each of the 4 candidates that we found. Like, think of the table as our little debate lecterns things. So in here we have, as candidates, we have -1, we have 0, we have 1, and we have 2. So each of those needs to get into the function so that we can actually figure out what those values are. So for instance, if we plug in -1, we're going to get 3 times 1 minus 4 times -1. That's going to equal 3 plus 4 is 7. Likewise, if we plug in 0, that's the easiest one. F of 0 is going to equal 0. I guess if you want to, I guess for sake of parallelism, I'll do that. If we plug in 1, again, these are pretty easy. You can tell I'm giving you some nice values here. I'm not going to try to burn you on it. We're going to get 3 minus 4 equals -1. And by the way, at this point, you can kind of see it changing as we go through. We're making comparisons as we go. So far, x equals -1 is leading in the race to become absolute maximum because it's so far produced the largest y value. Likewise, although 0 was leading the pack for absolute minimum there for a second, -1 entered the race and suddenly is even lower. So suddenly it's got a little bit more attention. It's a better candidate than the previous one. In fact, 0's just lost its ability to win any race. So bye 0. But finally, as we said, we need to check all of them. So we're going to compute f of 2. That's going to be 3 times 2 to the 4th is 16, minus 4 times 2 to the 3rd is 8. That's going to be 48 minus 32, which is 16. And oh, look at that. It's an upset in the final leg. Like, I don't know, they just hosted what are those things called? One of those weird election things. I can't think of it. My mind's tired. It's the middle of summer. What am I supposed to do here? So we just found those pieces. So we've now got all 4 y values to compare. And in fact, the fourth step is to simply make your comparison. Like basically, and when I do this comparison, I actually I have a kick out of doing this. I make the comparison, I look for the smallest one, and I label it smallest. Let's not overthink this. Minimum means smallest. And when I look for the maximum, I look for the one that says biggest. Now, of course, you could write min and max, but opportunity is pretty fun to say this. So from there, we've just made our comparison, so all that's left is to actually state it. Let's say the right things, like communicate your answer. So state your answer. And of course, this is one of those moments, we haven't done a whole lot about it since we talked about in the beginning, but if it said find the absolute maximum value, say, we need to state the y value. If it said the x coordinate of, we'd do that. In our case, it doesn't say anything, so we're just going to point out that our global or absolute minimum is going to be the point 1, negative 1, and our global or absolute maximum is going to be the point 2, 16. So those appear to be our high and low points. Now, of course, it's worth asking, though, is this actually the highest and lowest point that we ever get to? Well, a quick visit to Desmos would allow us to see that really fast. I can't spell. There it is. So let's go look at our graph here. So we are interested in, let's make sure I do this correctly, 3x to the 4th minus 4x cubed. And we were interested in the interval, I think it was from negative 1 to 2. Was that right? We'll find out. So let's see, projector mode, grid. So as far as our pieces, the minimum seems to be right there at 1, negative 1. And the maximum, it's not plotting for us, but you can see its shadow right up there. It looks like the maximum is at 2, 16. So it looks like we have indeed found the absolute extrema for this particular function. And again, all we did with the candidates test, it seems like crazy intense, but it's really not. All we did was find the critical numbers using the derivative and setting it equal to 0. You'll find later that's a pretty common technique in calculus. Second, we looked at the endpoints. Third, we made a quick table and made some comparisons of the y values at each of those candidates. And then finally, we just stated our answer, which is just like punching the ballot card and spitting out like the win. Well, I guess it's not just as simple as punching the ballot card. I guess there's more dynamics there. But metaphor aside, we got to our answer. This candidates test thing is a thing you're going to do many, many times. Okay, to wrap things up here, I do have one last problem for you to do as kind of a triad that brings a little bit of everything together, involves a little of everything we've done today. Before that, I just wanted to do a quick little verbal overview just to kind of hit things one more time before I release you to work on that problem, pause the video, and then come back to see what the solution is. So in here, let me point out to you a couple different pieces. First, we started by observing the fact that although it's easy sometimes to look at functions and determine their intercepts, it's sometimes hard to find their maximum values, like our relative high points and relative low points. Although it turns out that there does appear to be some connection between horizontal tangents, where the slope is 0, and those high and low points. We started by talking about local extrema, and how all you needed was an open interval for which that high point, or that point was the highest one, or the lowest one, depending on your case. We identified them on a picture, and then we recognized the need for some tool to find these guys. And it turned out that tool is critical numbers, places where the function's defined, but the derivative is either 0 or undefined. So we looked at examples for each. We recognized the theorem that pointed out that the relative extrema always occur at critical numbers. And then we looked through some different techniques that got us to critical numbers, including one that was a little bit challenging using a piecewise function. After that, we talked about the fact that although those are nice, they aren't necessarily the highest or lowest point on an actual graph. Instead, we wanted to talk about the global or absolute extrema, which could occur at the endpoints and are defined over a closed interval instead. Beyond that, we looked at some different examples how changing the boundaries or changing the interval we were on dramatically altered the presence of absolute extrema, and that led us to consider the extreme value theorem, which says that for a continuous function on a closed interval, there has to be a maximum and minimum. And we looked at why it was that that was true. But the outcome was that if we have a continuous function and we're analyzing it on a closed interval, we're guaranteed to get maximum or minimum. After that, we realized that we needed a little recipe to move forward, and that recipe was to realize that the maximum and minimum always occur at either a place where the derivative is 0 or undefined, or at one of the endpoints. And that led us to the tool which we're calling the cNotes test, which lets us, in a very organized way, identify all the places it might happen, which is just critical numbers and endpoints, by the way. And then we just checked their values and said which one's biggest and which one's smallest. We resulted to a comparison. And that leads us through the entire lecture that we've hit today. That covers everything that we're going to need about extreme values, with the exception of obviously applying this and hitting some different kinds of functions. So with that said, as I mentioned earlier, I do have one last little try it for you to bring it together. I'm sorry there weren't more try-its during the lecture. It's simply because it's the first one I'm having to make in preparation for surgery. So I'm just trying to get a feel for everything. At the same time, I think this is a good try to finish things off. So what I'm going to invite you to do is to, in just a second, pause the video, let everyone work for just a little bit, and then come back together and compare answers with the one that I found, and you'll hear a quick little overview of the question. So go ahead and pause the video now. Okay, so with that said, hopefully you've unpaused the video. We're going to take a look at the answer to this, and I'll just give you my quick overview. And of course, at any time you can pause and just let the solutions of the problem stand up. Very similar to the last one, but throwing in that piecewise wrinkle sometimes throws people. So with that said, here's my work. So we had this piecewise function. It was combining a line with a cubic. So once again, all polynomials all the time means that a lot of things are taken care of here. But from there, we were asked to find two things: find the critical numbers, and then find the global maximum and minimum of g of x on the interval from -10 to 3. So in here, the first thing I did was find g prime of x. I set each of the branches equal to 0, and I found that there were two potential critical numbers here, -2 and 2. But because both of them came from the cubic, which was only defined for positive values of 0, or non-negative values of 0, that meant that only 2 was actually one that we had to consider here. So you would have been okay, I think, if you included the -2 for your final answer, but it would have been incorrect for critical numbers. After that, we also had to check for the differentiability at x equals 0, the boundary point. So I checked the limits of both g and g prime. It turned out that it is nicely continuous there, allowing us to use the extreme value theorem to actually guarantee a max and min. But unfortunately, there's a sharp turn at that point because g prime equals 2 on one side and -12 on the other. So because of that, we have two critical numbers, 0 and 2. After that, we did the cNotes test by using the endpoints as well as those two critical numbers we found. It turns out that the high point ends up being at 0, 5, the global maximum by technical terms, and the smallest point ends up at -10, -15. So in fancy terms, -10, -15. To illustrate this, and I'll come right back and let you stop it, like looking at the function, there's our entire function itself. Kind of an interesting one. I don't know, let's see if we put it standard. There, I can zoom out a little bit here. So you can see there's our function itself. If we restrict the domain we are interested in, though, doing a little bit more work, we can see the lowest point is clearly down there at the left endpoint, -10, -15. And the highest point is that sharp turn. I mean, look at that. It is a sharp turn. Straight line up, parabola down and out afterwards. So it looks like we did everything correctly there. And of course, with that said, that completes our entire lesson for the day. Again, wish I was there. Since I'm not there, hopefully this was sufficient. And again, if you have any questions when you're doing through the homework, remember that there are video solutions there to support you as well. Otherwise, with that said, hope you have a great rest of your day. And thank you for watching and hopefully learning. Bye.